Yeah, great, perfect. Okay, so dear all, thanks for being here with us now, despite the difficult times as far as sports are concerned. So here's an update, so to say, on work we have been doing in the past years about the geometry of 3 alpha delta Sasaki manifolds. Now, of course, I will tell you what these manifolds are, and in particular, this time we're going to focus on the curvature properties, and I will try to explain to you what we have been doing in this and where we continue. All this is actually appearing in a series of papers, which I wrote with Giulia Dileo from Bari and my former PhD student, Leander Stecker, who is now a postdoc in Hamburg. Right? And the latest preprint on the archive is not that old yet. Okay, so let's get a start by looking at curvature operators. So we start with a Riemannian manifold. We consider its Levi-Civita connection. And we have, of course, the classical Riemannian curvature operator, a curvature tensor, which induces a curvature operator, which I view as a symmetric operator going from two forms to two forms. Right? Okay. And we do know that if the curvature operator is a positive operator, then we can conclude that the sectional curvature is positive. So if you can prove that this is positive, this would be a way to show that your manifold has positive sectional curvature. Unfortunately, things are not that easy because actually conditions for positive sectional curvature are rather little understood. Whereas for positive Riemannian curvature operators, things are clear because we have the theorem by Böhm and Wilking from 2006, which claims that if your manifold has positive Riemannian curvature operator, then it's actually locally a space form, meaning just a sphere modular discrete subgroup. So there's not much going on, right? And so our idea is to get conditions which would be sort of intermediate. Okay, good. So for this, we introduce the notion of strongly positive curvature. We consider the Bianchi map, which is the classical map, script beta, from symmetric endomorphisms from two forms to two forms to four forms by defining bet B of T being such a tensor, as 1/3 the cyclic sum of these combinations, right? And we do know that the kernel of B in the Riemannian case just corresponds to algebraic curvature tensors, and in particular, the Riemannian curvature operator would lie in there. And in general, we have the decomposition of symmetric endomorphisms as being the kernel plus the image of B. Fine. So now suppose take any omega which is inside symmetric endomorphisms and define for such an omega something which looks like a sectional curvature, right? For this endomorphism, the omega sectional something is just defined by the normal formula or normal expression we have, namely our metric evaluated at omega x wedge y, comma x wedge y, where the plane sigma is spanned by the two independent vectors, vector fields x and y precisely. And then it is a crucial observation due to Thorpe in the 70s that if omega is actually a four form, then the sectional curvature of the Riemannian curvature operator is just the same as if I add this four form omega to R. Right? So in that sense, omega does not influence my sectional curvature, but of course it does change this operator, R plus omega, right? Because omega wasn't there before. So this led to the following definition, namely, given a Riemannian manifold, we say it has strongly positive curvature if there exists an omega, a full form, such that the combination R omega plus Rg plus omega is a positive operator, right? And actually in dimension 4, this is equivalent to positive sectional Riemannian curvature, but in higher dimensions it isn't. It's not equivalent, but we do still have, nevertheless, if the Riemannian curvature operator is positive, then in particular, of course, M would have strongly positive curvature in the following sense, and then we could conclude that the sectional curvature is positive. So we have found an intermediate condition between these two extremes, and we want to investigate it. Other people have tried to investigate this, and we are going to add something on that. Right? Now, I will also have the condition of not strongly positive curvature, but strongly non-negative curvature, and strongly non-negative curvature will be for larger or equal. Okay, so basically allowing some zero eigenvalues as we go along. Okay, so obvious questions to ask. What manifolds do or don't have strongly positive curvature? Right, and the main reference on the topic is a very nice paper by Betziol and Mendes from 2018. Namely, most compact homogeneous spaces with positive sectional curvature actually have the stronger property of strongly positive curvature. But not all, and the main exception is actually the canonical. Okay, furthermore, strongly positive curvature behaves very well under Riemannian submersions. Namely, if I have pi from M to N submersion, then if M has strongly positive curvature, one can conclude that N has strongly positive curvature as well. So just as we're used to for positive curvature, which we also know to behave well under submersions, we have here a modification of the notion of curvature, which will also behave well. Okay, the second question we want to ask is, where do we get omega from? Right, this notion of positive, strongly positive curvature depends in an essential way on the full form. And in fact, in Betziol Mendes, when they prove their results, the full form is not constructed explicitly. So our guiding question long ago was actually to do some experimental mathematics to see whether one could describe this full form explicitly. And the motivation being, if I know a lot about the geometry of the manifold, it should be possible to see the full form from the geometry and see that it has a certain meaning. And from my point of view, this is the main contribution of this talk, namely it produces in certain geometric situations, which I'm going to describe, candidates for omega, and then we prove that omega basically works. Okay. So how do we get omega? This is really what we want to look at. Yeah, good. And last question, how is all that related to these infamous 3 alpha delta Sasaki manifolds, which already appeared in the title? And well, there is a famous theorem by Agricola and Hamburg that claims that there exist variations of 7-dimensional Sasaki manifolds with possible sectional curvature. Okay, different means, and Eschenburg, this was the biquotient approach, of course, of the time. And there exist variations in the sense it's not the Sasaki metric, but one deforms the metric, or what shows the existence of a deformation of the metric to conclude positive sectional curvature. So we knew that there would be some, we're looking at this huge class of 3 alpha delta Sasaki manifolds. Still don't know, but we do know that in this huge class, there are some examples of positive sectional curvature. So it's not totally stupid to think that there should be more, because actually these variations are 7-dimensional free alpha delta Sasaki manifolds. Okay, so let me tell you what free alpha delta Sasaki manifolds are. So free alpha delta Sasaki manifolds, the first thing to know is that these are a particular class of free contact metric manifolds. So we have a manifold of dimension 4n plus 3, Riemann metric, eta I, psi I, phi I being an almost contact metric structure. So that's what this ACM means, right? For each index I, these triples, eta I, psi I, phi I, just define almost complex metric structures on our manifold in the usual way. We have a splitting of the tangent space into a horizontal and a vertical part. The horizontal part being the intersection of the kernels of these three one-forms, and V is just what is spanned by the dual vector fields of the one-forms. Okay, so this is my vertical space. And the way to look at it is basically the following. So this is a subspace. The tangent space is 4n plus 3-dimensional. And on the picture, I'm only showing the vertical part, which is at 3-dimensional, so I can actually draw it. And I try to write the three vector fields, psi1, psi2, psi3, which are just the three red vector fields of these three contact structures, are orthogonal, right? And then here I have psi1, and to psi1, I have the orthogonal plane psi1 perp. And the idea is now that, so first, psi1 vector cross product with psi2 is psi3, inside V, of course. And secondly, in each of these perpendicular planes, I have a almost complex structure, phi I, right? This is what the phi i's are doing. So phi I in this plane is basically the almost complex structure, which in particular would map psi2 to psi3, okay, which is written here. And then you continue by permutating all these things. So in particular, in this plane, you have phi 3, and phi 3 will then change psi1 to psi2, and so on. Yeah, I like this picture as well, I have to say. This is my invention, trying desperately to get a grip what is going on. Okay, so I have that. And these are the compatibility conditions. And the structure group actually is reducible to SPN times three-dimensional identity. Good. So a free contact metric manifold now is said to be hypernormal if the Neuenhaus tensor of all free contact structures really vanishes. So they're integrable one dimension higher. And there are some remarkable classes inside, in particular the free alpha Sasakian manifolds, which just means that for each index I, each of these single structures is alpha Sasakian. And it's a free Sasakian manifold if this alpha is equal to 1. This is just due to the fact that a global constant rescaling of a Sasaki structure is not against Sasaki. So this alpha takes care of such a global rescaling. It's nothing more than that. Observe that it is well known that free alpha Sasaki manifolds are automatically Einstein. We have the class of free cosymplectic manifolds, which means each single structure is cosymplectic. Free quasi-Sasaki is each single structure. You guess it is quasi-Sasaki, etc. What all these definitions have in common is the observation that we do not impose any conditions on the relative behavior of the three single almost contact metric structures. We just impose that all three viewed isolated fulfill a certain condition. And the main idea of free alpha delta Sasaki manifolds is to link these three structures, to have some compatibility condition between them. Okay. Now, there's a classical theorem of Kashiwara, which said that if the structures are truly contact, so d eta I equals 2 phi I for all indices I, then the manifold is actually automatically hypernormal in the sense above, and one proves easily that it's free Sasakian. So whereas in if I only have one structure, this condition does not imply Sasaki. If I have three of them, it does. Okay, and this condition of hypernormality is a quite interesting one, right? It gives us better grip on these structures. Okay, good. So these is a setting of notions we had, and now let's go to free.
Sorry, just to be clear.
Yeah.
So the phi I are the sort of transversely Kähler two forms,
Yes.
yeah?
Right.
Okay, cool. Okay, right.
Yeah. Okay. Right, exactly. Phi I are the almost complex structures in the orthogonal complement of the direction psi I.
Cool.
Yeah,
thank you.
More questions? You just stop me, you know? I'm talking like into a black hole, like in all these internet talks. So if you ask a question or make a comment, I'm glad, because then I know that you're not all asleep or not all mourning the bad sports situation. Okay, good. So phi alpha delta Sasaki manifolds. They are almost free contact metric manifolds and phi I, psi I, eta ig, such that we have two constants, alpha, real, non-zero, delta, any real number, satisfying that the d eta I equals 2 alpha phi I. So that would be the normal contact condition we know from one-dimensional situation. But now we allow an extra term which mixes the three structures. Namely, it has this part eta j wedge eta k, right? Where ejk is any even permutation of 1, 2, 3. This condition has, so what I'm advocating is this is the right condition to look at. It's a very easy modification. It's the kind of modification which would not appear in dimension in a one if you only consider one structure, clearly, because we have this mixture. But this mixture just makes the things fit together perfectly and still give freedom to play around with these manifolds. Now, if alpha is equal to delta, this is an obvious special case, because then this additional term vanishes. And this would just be a classical free alpha Sasaki manifold. Observe that the phi i's are not closed in general, because the equation implies immediately that d phi I is proportional with this factor delta minus alpha to this form, these three forms here, right? And as it is reasonable to distinguish three main classes of free alpha delta Sasaki manifolds: the positive, the negative, and the degenerate case. The positive case corresponds to alpha times delta positive, negative alpha delta negative, and degenerate, well, degenerate if delta happens to be 0, which is possible and which is very special. And our colleagues here, Oliver Goetsch's, together with Leander Stecker and some other PhD students from Marburg, they published a separate paper only on the degenerate case, which I really recommend. It's nice reading, right? Degenerate is hard to achieve. The poster example are quaternionic Heisenberg groups. Okay. I will explain in a second why positive and negative is the right way to distinguish these things. But first, let's give a theorem which summarizes a few properties of these three alpha delta Sasaki manifolds. The first thing is we can prove that these structures are also hypernormal. So that we have a generalization of Kashiwada's theorem, which was coping with the case alpha equals delta equals 1. Secondly, the distribution V is integrable with totally geodesic leaves. And each of the vector fields psi I is automatically a killing vector field, which is a condition we know well from Sasaki geometry. So it's not an assumption, it follows just from this one equation. And furthermore, we have a geometric interpretation of the second constant delta, because delta tells us how the three Reb vector fields, what their commutators are. So the relative position, so to say, right? And here we see why delta equal to 0 is so special, because delta equal to 0 means that the three Reb vector fields commute. So it's like having a three-dimensional abelian factor, right? Whereas in all other situations, I have a copy of SO3 at the Lie algebra level, or of SL2, compact and non-compact three-dimensional semi-simple Lie group, right? And that explains why delta is an important quantity, really gives the geometric interpretation, and why we parameterized our equation with this alpha minus delta. Okay. Here are some formulas. Now, there's no exam afterwards to learn these formulas by heart, but it's just to tell you that you can make things extremely explicit, right? For example, the Levi-Civita co-derivative of the Reb vector fields can be computed in terms of alpha, alpha minus delta, and so on. And in the papers, you will find many formulas of that type, right? Because without them, all the theorems would not be possible to prove that I'm going to present you, but you are lucky. This is only one of the very rare instances where I will show you some formulas. And for everything else, I refer to.
Can I just real quick?
Yeah, sure.
In terms of examples,
yes.
What is your canonical example for 3 alpha delta Sasaki? Is it you get from self-dual forms over a Kähler surface or something?
You have tons of examples. So wait. Yes. Give me one more second. I will explain you where the examples come from. And actually, the talk could just be filled now with examples, but then we don't get to curvature. Okay. Yeah. But I will give you the following tells you, you will see in a second where the examples come from. Okay. So these metrics admit very nice deformations. So we call them H homothetic deformation because they are along the horizontal and vertical subspaces. So write down the metric like that, okay, and rescale to a new metric with factors A and C squared. That's just notations. And take the new vector fields, Reb vector fields scaled with 1 over C, whereas the almost complex structure stays what it is. Okay. And then you compute, and you realize if you do H homothetic deformation of an free alpha delta Sasaki manifold, it is again a free alpha delta Sasaki manifold, but the parameters alpha and delta are modified. You become some alpha tilde and delta tilde. And alpha tilde is just, marking formulas is not so good. Wait a second. Should have some marker here. Let's try. Yeah, zack, voila. Okay. So we do have a formula for how to change alpha and delta. And we see, so alpha tilde becomes scaled with C over A, whereas delta is scaled with 1 over C. But that means that the sign of the product alpha times delta is not changed because the C cancels out and the A, and this was forgotten to be written somewhere, but A has to be positive. Okay, it's sort of obvious that it has to be positive because otherwise it wouldn't be a Riemannian metric anymore from this formula here. But we really assume A to be positive. Okay, so we see that the sign of alpha delta is preserved, and that also explains why it makes sense to distinguish this positive, negative, and degenerate case. And it means that if you start with a free Sasaki, or the other way around, if alpha times delta is positive, then you can always deform it by such a homothetic deformation into a free Sasaki. So the upshot is any free Sasaki manifold is going to give you tons of examples for the positive case. Konishi bundles and all that will give you examples. We classified in one of the papers all the positive homogeneous examples. The positive homogeneous examples are just what you would expect, namely very close to the classification of homogeneous free Sasaki manifolds. And for the negative case, I'm going to tell you in a second what we did. Okay, good. More questions on that? Good. The second tool we need is we need a good connection. Now, those of you who know me better know that for many years, almost decades by now, we have been working on metric connections with non-vanishing torsion. And you see the trouble here with these 3 alpha delta Sasaki manifolds and already with 3 Sasaki manifolds was that you have a characteristic connection if you have a good reduction. But free contact structures are not defined by a reduction of the structure group. And it doesn't work to define them via a reduction. And so one needs another approach to get to a good connection. So in this paper, we explained, or we tried to go from the most general case to the special case. And the upshot of the paper is that there exists a unique connection, Labla metric with skew-torsion, such that this equation here is fulfilled. And beta, we allowed beta to be a function, but it turns out to be the constant, and a constant actually which you can compute immediately from delta and alpha. Now, this equation might remind you of something. It is too strong to require that these quantities vanish so that the phi I are parallel. This is what you would like to have, but it's unfortunately not possible, right? For reasons explained. But it is possible at least that the derivative of phi I will again be a linear combination of the phi i's. This is what it means geometrically. So basically, this distribution spanned by the 3 almost complex structures is invariant under my connection. And so we mimicked here the condition for a quaternionic Kähler structure. Right? This is the philosophical explanation why this condition is good. Okay. And then the year afterwards, together with Leander Stecker, we proved the following. Whenever I am in this situation, there exists a locally defined Riemannian submersion pi called the canonical submersion of a 3 alpha delta Sasaki manifold along this vertical space we had defined onto a quaternionic Kähler space, which I'm always going to call N. Right? And the quaternionic Kähler structure is just what we would assume, namely it's the projection down of the phi i's, which were part of my free contact structure. Right? Furthermore, this submersion basically for lifts of vector fields basically means that the canonical connection induces the Levi-Civita connection on the base. Right? So this connection really captures in a right way the geometry I have to put on top to get something nice on the quaternionic Kähler base. And so we see if you have a favorite quaternionic Kähler space by inverse constructions, you can get 3 alpha delta Sasaki manifolds. Now we do know a lot about quaternionic Kähler spaces, because now let's have a look at what the scalar curvature is doing. Now this framework with alpha and delta has the really nice property that things can be computed very explicitly. So we have here that the scalar curvature of the quaternionic Kähler base is up to some constants proportional to this number alpha times delta. And that implies again that I have again these three situations to consider, namely this quantity larger 0, smaller 0. I have to draw with my right hand, but I am a left-hander, so this is very complicated. N equal to 0. And it explains us why things are so difficult, because in the positive case, things are fine. We have positive scalar curvature, quaternionic Kähler symmetric spaces, the classical Wolf spaces, and they really yield nice examples of manifolds. In the case that the scalar curvature, or the scalar curvature of the quaternionic Kähler space vanishes, it is a hyperkähler space. Hyperkähler vibrations are much more complicated than quaternionic Kähler vibrations, which are not hyperkähler. So that explains why this degenerate case, delta equal to 0, right, will yield some really different geometry. Hyperkähler converse as an opposition to quaternionic Kähler. And finally, last situation, we have here this negative case. So alpha times delta negative. So what quaternionic Kähler spaces with negative scalar curvature do you know? Well, the symmetric partners of the Wolf spaces, and then all this bunch of new constructions of Alexievsky and Cortez. And we were able really to construct examples of 3 alpha delta Sasaki manifolds whose quaternionic Kähler base is a non-symmetric Alexievsky-Cortez space with negative scalar curvature. And the first example which occurs is in dimension 19. Okay, so this is hard stuff, but feasible. Okay. So here come these are the examples. But
sorry, so if you want to mass produce examples, they'll typically be non-compact, right?
In negative case, yes. In negative case, they are typically not going to be compact. And actually, compact is really difficult to achieve, which was proved also in this paper for the degenerate case, the hyperkähler case.
Right. Yeah. Okay.
Absolutely. Yeah. Okay, good. Now we want to connect curvature operators, right? We have a geometric setup. This is our playground. We want to see whether we can actually construct a 4-form omega, which is going to make everything strongly positive curvature operator. So we have a canonical connection. It is metric. It has parallel skew-torsion T. So let's look at the curvature operator of this connection. You compute it and compare it to the Riemannian curvature operator. Then you see the Riemannian curvature operator equals Nabla curvature plus 2 extra terms which really have different behavior called script G, script S. So script G comes from the torsion form and is defined by being basically this square term of the torsion form, which in particular is symmetric in the 2 arguments. And S of t comes from the 4 form, which is associated to my torsion, right? So the torsion T has a 4 form, which is dt. And this dt appears all over the place in geometry of connections with skew torsion. Sigma t captures a lot. It measures basically how non-degenerate the torsion is. And so from this sigma t, there is this endomorphism S of t derived. And actually, when we started, our idea was we know from other manifolds that sigma t catches a lot of the geometry. So the question was, is sigma t the right 4 form to look at, right? So start with a manifold. It should have a good characteristic connection with torsion t. Take the differential of the torsion. That was our candidate for the 4 form in this approach of strongly positive curvature. And the answer is, well, basically yes, but not exactly. But almost, philosophically, yes. Okay, so the naive idea of our approach is if we can show that the Nabla curvature operator is positive, then we rewrite things like that. And since GT is positive anyway, which is observed here, then we would be able to conclude that M has strongly positive curvature. So it's not working exactly like that, but the idea is not that bad either, right? So this assumption is too strong, but we can connect another curvature operator to the Riemannian curvature of the base, this quaternionic Kähler manifold. And that actually works very nicely. Okay, let me tell you something about the easy case. The easy case is do not have strongly positive curvature, but just strongly non-negative curvature. There, the computation is really easy, and you prove if you have a homogeneous phi alpha delta Sasaki manifold. If alpha times delta is negative, then the curvature operator is non-positive, and so end of the story. But if alpha times delta is positive, then R is non-negative if and only if alpha times beta satisfies this equation. And this beta, remember, it was delta minus 2 alpha, something like that. So one can write it down very easily. Okay. However, strongly positive curvature is much more difficult to achieve. Okay, yeah, here it's a summary. So positive homogeneous phi alpha delta Sasaki is strongly non-negative. And the full form, yeah, well, you see, we start to see that we have to modify it a little bit. There's a factor minus 1/4, but that's just a convention. Okay, but sigma t was the right candidate to look at under that assumption, which was given here already. Okay, good. And now the main result of the talk I want to show you, and worst case, we stop when the gameplay starts, is the following, namely, so let M be a phi alpha delta Sasaki manifold with canonical submersion just as before. Assume that the base, our quaternionic Kähler base, has strongly positive curvature with respect to a certain four-form omega acting on the quaternionic distribution and with minimal eigenvalue some mu. Okay, which actually I could have deleted because it doesn't appear anymore. And if delta over alpha is large enough, much larger than 2, my manifold is strongly positive with four-form given by, well, sigma t, philosophically, as I said before, the minus 1/4, which I had in the slide before, remember, still has to be modified by a little epsilon, which is here. And then I have to take the inverse image under the projection of omega, pi being the submersion. Okay, the four-form acts on the base. And this is really possible to achieve. You see, in my previous theorem, this theorem is so nice because I'm restricting attention to the homogeneous case. If I'm leaving homogeneous, where everything can be computed explicitly, if you know the candidate for omega, right? Whereas here, I have no assumption of that type. And in particular, corollary is that the 7-dimensional phi alpha delta Sasaki manifolds with positive sectional curvature actually do have H homothetic deformations with strongly positive curvature. So the two notions really correspond. Okay, I'm not sure whether I should say something about the proof. So the proof is complicated and you do go through it. I'm at the moment considering that there's a game starting and I wanted to tell you a bit more about other things. I think I will skip the proof. But this proof, I mean, philosophically, what are we doing? You have to look at these curvature operators and split them in a clever way in components, deal with components, put it back together and check that you didn't destroy anything. Okay, good. So maybe I just skip that, right? And we go on to more interesting stuff. So strong positivity is much more restrictive than strong non-negativity, as I said before. And strong positivity is the only thing which really implies strict positive sectional curvature. Now, the homogeneous case is not that new because homogeneous manifold with strictly positive sectional curvature have already been classified. This is due to Warlock and Berger in the 70s. And then one has a look which of them actually admit a free alpha delta Sasaki structure. And we see that we have the Alaf-Wallach space in dimension 7, spheres of dimension 4n+3, and real projective spaces. Okay, so the theorem which was known before qualitatively but not explicitly is that the free alpha delta Sasaki spaces, which are the 7-dimensional Alaf-Wallach with this 4 form for some small epsilon, as well spheres and projective spaces with a 4 form which looks like that, right, are strongly positive if and only if alpha times beta is positive. Where's the difference? Well, for the Alaf-Wallach space, we can prove that we can choose omega to be 0. And for spheres and projective spaces, we can say explicitly what to take, namely it's a version of the sigma t, which is then restricted to some subspace, whatever. So we can write down, you see, it depended on this 4 form on the quaternionic Kähler base. And now if you want to apply the theorem, you need to find examples where you can make it happen. So this is the situation. Now, how do we get results like that? Well, basically by looking at the paper we wrote before, in which we describe anything you ever want to know about the curvature of free alpha delta Sasaki manifolds. And I invite you to have a look, because you don't have to do the calculations again. We checked and cross-checked them. Now you have tools, right? And so I want to show you qualitatively what kind of results we are proving to get here, so that maybe in other geometric situations, maybe you're not interested in strong positive curvature, but you may be interested in the tools we're using. So the tools are basically eigenforms of the curvature operators, because we need to diagonalize them and to then see what the eigenvalues are. Okay, so if we look at the canonical submersion pi, and at horizontal lifts of vector fields, then one key formula is to say how the curvature operator upstairs on for the canonical connection links to the curvature operator of the base plus some additional term. And this additional term we can really describe, because the phi i's are just the 2 forms associated, so the Kähler forms coming from the little phi i's. Okay, so it's as explicit as things can be. And on the quaternionic Kähler base, we can describe again these operators, at least when they act on the horizontal part. So this is what this H means. H is horizontal part of these Kähler 2 forms, right? Because we can just compute that this is again 4n alpha delta times this horizontal part. Explaining again how we get our formula for the scalar curvature of the base. Okay, so we get expressions like that. And a lot is known about the curvature operators of quaternionic Kähler manifolds. And for example, we get results of the following type. The curvature operator of the curvature admits 6 orthogonal eigenforms, which are things like that, with eigenvalue 2 alpha beta times n plus 2. Here are some eigenforms which have eigenvalue 0, and this 0 is really, you know, a pain in the ass, to say it frankly, because these zeros destroy strongly positive curvature. That's not so kind of them, but that's how it is. And then so we split the curvature in these terms and build up everything, and if you find enough eigenforms, then you're happy, right? One nice outcome is, for example, a theorem like that. For the Riemannian curvature operator RG, the following conditions are equivalent. These 2 forms are eigenforms. Okay. Or each of these 2 forms is an eigenform, or the manifold is Einstein. And the condition of being Einstein is again something we can very easily describe. The 2 Einstein metrics correspond either to delta equal alpha, but this is just the free Sasaki case, right? Remember, delta equal alpha is free Sasaki. And this metric, again, It was known before that any free Sasaki manifold admits a deformation of the metric, which is again Einstein, but not free Sasaki anymore. So this free Sasaki was isolated, and then you deform the metric, and you know somewhere is another metric, which is Einstein. Now we can put the two geometries together and just parameterize them by alpha and delta, right? And you deform homothetically as you like. And so you can describe these families of metrics in one bunch, which we did also. And if delta is equal to alpha, then the 6 eigenforms admit the same eigenvalue, which is just alpha squared. Okay, that was the end of the talk. We have like 20 minutes to discuss a few things and answer questions. But before we go to questions, here comes the advertisement section. You know, when you're watching the football game, you also get advertisement. Now you also get advertisement here. The advertisement is that finally, after so many years, we are having again a conference in Rauischholzhausen, which is a little cute castle very close to Marburg, where we have had many conferences in the past. And then came the pandemic and other problems. But finally, again, in August next year, we are going to have a one-week meeting there again. Right? And I invite you all to come and visit us at that occasion. In particular, if any of you are going to Münster, because next year is again, you know, the year where there's this curvature conference in Münster, maybe it's worth considering arranging your plans in such a way, go to Münster first, have a week of vacation in between, and then come to Rauischholzhausen for the conference there. Well, the organizers are the usual suspects. It's me, Oliver Götzsches, Taki Constantis, our postdoc, Pablo Ramacha, well known to many people in Cordoba, and Louis Jos, who was a postdoc in Marburg for many years. Thank you very much for being with me on such a day.
Thank you. Let's thank the speaker. All right. So we have 7 minutes for questions, comments. Adrián?
Sí. Yes. Okay. You know, Ilka, about this condition of the curvature tensor being positive, is it known when that happens on homogeneous manifolds?
Well, the main reference is the Betziol-Mendez paper. But again, I mean, they look at the homogeneous case. The homogeneous case is basically settled, but they didn't describe the four form explicitly.
Okay.
And we give you the four form.
Okay,
right?
Good.
If you play around with these free alpha delta Sasaki manifolds, it becomes more or less obvious what the four form should be. You know, if it says, if you look at the homogeneous case, after all, why should it be any weird four form? It has to be a globally defined isotropy invariant four form. And there are not too many of that.
Okay.
Right?
Okay, great. Thank you.
Yeah.
Okay. Any more questions and comments? Yeah, maybe I'll ask something. So if we are maybe two questions. Let's say so in the 7-dimensional case, so n equals 1. If you were to whenever you have a 3, sufficiently good 3-something structure, this will give you a G2 structure, right?
Yes.
So what is do we understand as of now the relation between alpha delta 3 Sasaki and G2 in terms of the torsion? How does that go? All right, cool. How does that go?
So you have to see how we got the idea that a free Sasaki manifold would admit a larger family. So I said here already this situation, right, that every free Sasaki manifold admits a second Einstein metric. Now, if my manifold is, if you are in dimension, which I want to type text, yes, okay. So if n is equal to 1, right? So we are in, so we are in dimension 7.
7, yeah.
Yes. Then the second Einstein metric, okay, is actually not any Einstein metric. It is an Einstein metric which comes from a nearly parallel G2 structure. Okay.
Yeah.
And how did we get there? Well, we started all our theorems we first had in dimension 7, because how to the main, this is it's not visible anymore, but this is much more a theory or a class of manifolds which is about examples than one sees in this formal approach. What we did first is we proved that in dimension 7, any free Sasaki manifold has a nice parallel G2, nearly parallel G2 structure. This one coming from the from the second Einstein metric. Okay, a nearly parallel G2 structure actually has a characteristic connection because it's a G structure. Comes really from a reduction. Then we looked at the connection associated to the G2 structure and realized that it also had nice properties for the original structure we started with. And by this detour, we constructed the canonical connection. The second example, which we had, were quaternionic Heisenberg groups. Now, it's getting late here, over here. So, because a quaternionic Heisenberg group is a naturally reductive space. So it has an Ambrose-Singer connection. And the Ambrose-Singer connection, it has parallel torsion, parallel curvature, and it just happens to have skew-torsion. So the Ambrose-Singer connection of a quaternionic Heisenberg was the second example of a good canonical connection. Okay, and that's how we proved. So we had these two isolated examples, and the 7-dimensional was absolutely crucial, right, to see that we can do more. And in dimension 7, in the first paper with Giulia Dileo, we really discussed the 7. There's a whole section only devoted to the 7-dimensional case, in which we describe that you see, no, the other way around. Dimension 7, G2. G2 is defined by a spinor, right?
Yeah.
And so if there's a G2 structure, there's a spinor. So the spinor should have a meaning. And the meaning of the spinor is, first, the spinor is now parallel for the canonical connection. And now you do the following thing. It's really beautiful. I will just type here. Okay, you define, no, I cannot type, I should write. Okay, so you have a spinor in dimension 7, you have a spinor which is parallel. You look at the products psi I times psi. Okay, so the G2 structure yields the spinor. And now you define 3 new spinors by taking the Clifford product, Rib vector field times psi.
Okay.
And these 3 spinors, they are killing spinors. Because the old theorems of Thomas Friedrich and Ines Card said that a free Sasaki manifold in dimension 7 admits 3 killing spinors. And so our approach with this structure first explains where the killing spinors come from, namely they come from the G2 structure. And secondly, we have a uniform description why it's 3 spinors, because they are generated by one master spinor, this psi. And then if it's just not 3 Sasaki but 3 alpha delta Sasaki, they are generalized killing spinors. And they also exist on the quaternionic Heisenberg groups. So it's, you know, there are ideas for many things coming together at this place.
Wow. And finally, okay, this is really interesting.
It's really a synthesis of many things. Yes.
And so my second question would be this: there's a current, let's say, a beginning of a fashion to try and find solutions to this, G2 Strominger system, right? Where you not only need a G2 structure, but from it you also essentially need some sort of natural good connection on the tangent bundle. It appears to me that these alpha delta families come with these preferred connections.
Yes, G2
so
structures also come with a preferred connection, but one has to be careful because they typically want connections which have closed torsion. Not only, but so yeah, Jorge will remember we have had many discussions about this at different.
Oh, not quite. You see, not quite. If the torsion is closed, then you get the this what's called the exact algebraic thing, right? But if it's not closed, it can still satisfy this kind of anomaly condition non-trivially.
Yes.
So long as you endow the thing with a gauge bundle, but because several of your examples are, have this fibration structure, like this submersion, then the natural gauge bundle would be to just pull back the tangent bundle of the base space. And everything, it looks like the two things would be comparable. And you could try and
sure that they are. And in fact, if you look at what we did in the past years, but this is like 10 years ago, we had some results about the Strominger equations. So we some of this we have done. Now maybe they're probably modified a little bit, so one would have to check what the current fashion is exactly. I haven't been keeping track like in the last year or one or two what exactly they're interested in. One thing to observe is that if the torsion is parallel, then this four-form sigma t, which is algebraically always defined from t, is just twice dt. And unless your manifold is a Lie group, this is never going to be zero. Right?
Which but that's fine.
Right? So if that is fine, then it's wonderful. Then I assume this is the way to go. Yes, I'm pretty sure about that. And as I'm saying, we have had quite a few papers already in which we did the basics on these equations. For example, I remember there have been these people in Hamburg at DESY working in superstring theory around, oh God, what is the name of the colleagues? Okay, forgot the name, but exactly, it doesn't matter. Okay, so like 10 years ago already, they came and asked, okay, we take a Joyce manifold, which we know has parallel Riemannian spinors. Is it possible to deform the spinors in such a way that they would satisfy the Strominger equation and be still parallel for the new connection with torsion? And the answer is, in that case, when the manifold is compact, for example, the answer was no. So things like that we have done. I can send you some old slides actually, which summarizes a little bit what we have been doing. And if you can send me some new references, I can check how that fits into the old world.
Okay, thank you so much. I just plugged into the chat a link to these two lunatics, but basically what the authors do is they summarize what they think is the recent status of the fashion in terms of Strominger system. So the introduction explains how the problem has begun, and the examples constructed there are Sasakian, right? And the thing we just tried to do, and then we found out that there was another group doing, is precisely a 3 Sasakian type of situation. So we know it should be even more likely to be successful there. Now you have this extra freedom because you have this extra parameter delta that gives you a lot more leeway, and so this sounds very promising. If you maybe have a look at the introduction of this preprint, it explains the problem with all the contemporary degrees of freedom. And if you could send me, refer me to your previous work where you thought about this before, I could also have a look.
Sure.
Wow.
Okay.
Okay. Very cool.
I will have a look, and yeah, and we, you know, the worst thing is we continue discussing this in May. May? Yes, I think May.
Yes, yeah, I'll prepare for that.
Absolutely. And not only I'm coming, I'm bringing my 2 PhD students with me. So that'll be fine.
Excellent.
I will be happy to send you something. I will try to still do it. But you see, you guys, I am traveling over Christmas, and I will be away from my email. I mean, I guess it's also summer holiday time for you all, right? So I will be on holiday as well from December 15th, which is weather close, until January 10th. And I will not read any email in between because my new partner and I were going to the, I guess you call it, Islas Malvinas.
Aha.
So
all right. So let me then take the freedom to also advertise in the chat. It's very fresh announcement of this meeting we're gathering in France in June 2023.
Okay.
Which is also an opportunity to discuss some of this. It's being organized by Eric Lebeau. Oh no, it cut down my announcement in half.
Yeah, is there a web page already?
Yes. Yes.
This
is it. This is it. I think we can stop recording by now, Luis.
In
any event. This is it. So just warming up. This is a very, very fresh announcement.